Hi students, in this final video for online lecture 22, we are now going to talk about kinetic molecular theory. So what is kinetic molecular theory? These are rules that are going to govern the behavior of our gaseous particles. So let's look at the first one. A gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. The molecules can be considered to be points, that is, that they possess mass but have no appreciable volume. So what this rule means to us is that this will help us describe the compressibility of our gases because there is a large empty volume with a small point which we can consider our gas molecule. So this will help us talk about many of the ideas that you'll see here in a moment. Our second rule states gas molecules are in constant motion and in random directions. They collide frequently with each other. Collisions among these molecules are perfectly elastic. This is where we get our pressure from. Pressures are going to be exerted by the collisions of our particles, not only with themselves, but with the container in which they are kept in. The biggest assumption is that those collisions are perfectly elastic. Elastic meaning that there is no energy loss. This is a huge assumption. Our third rule states that gas molecules can exert neither attractive nor repulsive forces on one another. This means that they do not interact. Due to the large distances between them, there is not going to be any attraction or repulsion between our molecules. However, as we are going to show you with the Van Hoff equation and our intermolecular forces, there is going to be attraction and repulsion. Finally, the average kinetic energy of the molecules is proportional to the temperature of the gas in kelvins. Any two gases at the same temperature will have the same kinetic energy. This will be helpful to us when we are starting to look at some of our gaseous behavior. This can be summarized by our kinetic energy being equal to 1/2 mv squared. So if the kinetic energy is the same, we are going to have different velocities because our masses are going to be different for different gases. So let us take a look at how kinetic molecular theory talks about the compressibility of our gases. Well, using our rule 1, it is important to note that compressibility is only allowed when we have large distances between our particles. Using rule 1, which says that there is a great space between our individual molecules, and if we exert a pressure upon them, those distances can still be closed, but still to a point in which those molecules do not interact. Let us now talk about Boyle's law. Remember that Boyle's law talks about pressure and volume. The pressure is now going to be considered proportional to the collision rate with the boundary of our container. So what does that mean? Well, the collision is going to be equal to our number density, and our number density is going to be inversely proportional to our volume. So when we are talking about our molecules being in random motion, they are going to bump into each other, and if we reduce the volume, those collisions will happen more frequently, thus giving us a higher pressure. Now we can talk about Charles' law, which said also that the pressure is proportional to the collision rate with the wall. And now we are going to say that the collision rate is proportional to the average kinetic energy of the gas molecules. So this means that if we increase the temperature, we are going to increase the pressure. So as those molecules are moving faster due to more energy, they will have more collisions with other particles or the side of the wall, thus giving us a greater pressure. For Avogadro's law, our pressure is going to be proportional to our collision rate with the wall and the other molecules once again, and it should be stated that the number density is going to increase because I have more moles of my gas. The more moles means that there is going to be a higher number of collisions due to the abundance of molecules, and this is going to lead to the higher pressure. Finally, we can talk about Dalton's law of partial pressures. Molecules do not attract or repel one another are going to be able to help us give a accurate and summative amount of pressure between our mixture of gases. We will show you that this is not always correct. The pressure exerted by one type of molecule should be unaffected by the presence of another. If there are no attractive or repulsion forces, it does not matter based off the identity of the gas. They just know that those gas molecules can interact but remain unaffected. So this is how we get the assumption to allow us to have the pressure total be the sum of the individual pressures. However, as I will show you here in a few slides, that is not actually correct. So let us go talk about some of the behavior you would see using our kinetic molecular theory. The first thing we need to talk about is what is called our root mean square velocity. Notice that if I have nitrogen gas at 100 Kelvin, as I go and increase the temperature, notice that the distribution of my gas particles exerting a particular speed is going to get faster. I went from approximately 200 meters per second to approximately about 350 meters per second, and now at 700K, you are seeing a velocity of almost 700 meters per second. So as our temperature is increasing, we are seeing a majority of our gas molecules increase its velocity using the Boltzmann distribution. But now the interesting part is that if I were to go and take gases at the same temperature that have different masses, you will also see an important relationship. Notice with my chlorine being the most massiest of my gases, it is going to have the slowest speed because it has the greatest mass. This is using the fourth rule when discussing our kinetic energy. As you can see with nitrogen, as I am getting lighter with my gas, it is getting faster. And finally with helium, as you can see here, it being the lightest of the three is going to be the fastest. How I calculate this root mean square velocity is using the equation, the square root of 3 RT over my molar mass. This is a very important equation, but there is going to be some very, very critical units that you must need to know how to use, and I will show those to you in the next example. Calculate the root mean square velocity of helium atoms and nitrogen molecules at 25 degrees C. So how do I do this? Well, the first thing that I need to do is go and get my equation. So that is my root mean square velocity is equal to 3 RT over my molar mass. So as I said in the previous slide, we need to be very careful about certain units. Our R in this case, because we are wanting to deal with our joules, which is the kilogram per meter second squared, you are going to see that my R is actually going to be 8.314 joules per mole Kelvin. The reason that this is the case is that if you were to go and say that I have 1 liter atmosphere for every 101.3 joules, you will end up getting 0.08206 liter atmosphere mole Kelvin. This is the same ideal gas constant. But because we are dealing with joules, which contains our kilograms, meters squared per second squared, we need to leave it as 8.314. Also, this is going to give us the importance of having our molar mass in kilograms. So our temperature in this case needs to be in Kelvin. So that is going to be 298 K, and our molar mass First, let us go and deal with nitrogen. Remember that that is going to be 14.01 grams. We need to multiply that by 2 because it is a diatomic. So that is going to be 28.02 grams. But what we need to do here is go and divide by 1,000 to get kilograms. So in this case, you will get 0.02802 kilograms. So what I can do now is go ahead and solve for this equation. So I have 3. Now I'll have my R, which is 8.314 joules per mole Kelvin. And then my temperature of 298 K. And then finally, we can go and get our denominator, which is going to be 0.02802 kilograms. If I put this into my calculator, you will see that the velocity of my nitrogen gas is 515 meters per second. So now we know the velocity of our nitrogen. Let us go and do the math for our helium. But let's take a look at the helium. This is a smaller atom, so we expect it to go faster. So in this case, we will do our root mean square velocity is equal to the square root of 3. We still have the same R of 8.314 joules per mole Kelvin. We have the same temperature, which is 298 K, but now our denominator of our square root fraction is going to be much smaller because of it being helium. So our molar mass of helium is 4.0026 grams. We can divide that by 1,000 and get 0.0040026 kilograms. And if we put all of this work into the calculator, you will get a velocity of 1,360 meters per second. Notice that as I have a smaller gaseous gas, it is going to go faster. Another important behavior that you're going to see is what we call gas diffusion. This is the gradual mixing of molecules from one gas with molecules of another based off of their kinetic properties, which means their velocity and their mass. This should be random. We talked about this when dealing with our kinetic molecular theory rules. But let's take a look at 2 gases here. You are seeing ammonia, which has a mass of 17 grams per mole, mixing with our hydrochloric acid at 36 grams per mole. So which one is going to move further? Well, as you can see in the picture, we will get our ammonia chloride much closer to our HCl because our ammonia can travel a much further distance because it is going to be lighter. The lighter that a gas is, historically, the faster it is going to move. So when we talk about faster, we need to talk about rates. So as you can see by this equation of R1 over R2 is equal to the square root of molar mass 2 over molar mass 1. So using this equation, we would see that our HCl, being slower because of its mass, is going to travel less distance, and that is why you see the vapor cloud there much closer to the bottle of HCl. The other behavior that uses this equation is gas effusion. This is a process by which gas under pressure escapes from one compartment of a container to another by passing through a small opening. This is the behavior that we see when we have a car tire being punctured and a small hole leaking out the air. So we are able to go and use the same equation, but it is actually best to look at this a different way. A rate is a certain distance over time. So now, as you can see here, if I go distance 1 over time 1, and I were to do rate 1 over rate 2, I'm able to make one equivalency here saying that my distance is going to be the same. If my distance is going to be the same, I can cross them out, and you will now see that T2 is in the denominator of a denominator, and that is how we end up getting our T2 at the top with our T1 on the bottom. This is a much better format for us to use. So as we're going to do the next problem, we are going to want to use T2 over T1 equals the square root of molar mass 2 over molar mass 1. So let's take a look at this example. A flammable gas made up of only carbon and hydrogen is found to effuse through a porous barrier at 1.5 minutes. Under the same conditions of temperature and pressure, it takes bromine vapor approximately 4.73 minutes to effuse through the same barrier. Calculate the molar mass of the unknown gas, and we can do a suggestion of what it might be. So let's take a look and see how we would do this. So if I have T2 over T1 equals my square root of my M2 over M1, now I need to go and solve for those variables. So my T2 is going to end up being my unknown species. If that is the case, I can say that I have 1.50 minutes over my other time, so that is going to be 4.73 minutes, which is equal to the square root of my unknown mass, which we will call x, divided by our molar mass of our bromine vapor. If I go and look at that, that would be 159.808 because it is Br2. And if I put this into the calculator, I would get a molar mass for X being 16.07 grams per mole. Well, seeing that carbon has a mass of 12 and hydrogen having a mass of 1, we can approximate that the gas that we were using was CH4, which in this case is going to be methane. So as you're working on problems with diffusion and effusion, you are able to use both types of the equation. But in many cases, the T2 over T1 is going to be much easier for you to use. The last topic that we are going to talk about is that all gases aren't ideal. So for our ideal gases, we will use PV equals nRT. For our moles, we would make that equal to PV over RT being close to 1. So as you can see, as the pressure increases on the diagram on the right, our blue line is going to stay constant as the pressure increases. However, as you can see with our methane, our hydrogen, and our ammonia, this is not the case. So as we are going and looking at that behavior, you are seeing that the pressure is going to change the behavior. For our case of our ammonia, notice that the number of moles at a lower pressure decreases greatly and then has a linear relationship. So the question you have to ask yourself is, when does a gas exert the most ideal behavior? This is at low pressures and very large volumes. For low pressures, they do not interact, there is no attractive behavior, and they have space to behave like they want. For a large volume, that is the same thing and opposite of our low pressure, so therefore, it is going to have the same effect. When it comes to the temperatures, we also want them to be very high temperatures for the fact that that is going to give us the best chance of having elastic collisions in which there is no energy lost when those collisions happen. So the nice part about this is that if we look at our graph here, you will see that if it falls below the ideal line, we will call those the attractive forces. Once we go above the line, that is when we know that we have put so much pressure on our molecules that they are now going to be repulsed by each other. What this does is takes our PV equals nRT, and we are going to convert it to the van der Waals equation. This is for non-ideal gases. So as you see here, we are going to correct for the pressure by having what is known as the A term. The A term is going to describe the volume of a certain species and its interaction with each other. So as you can see with the A term, we have atmospheres times liters squared per mole squared. So this is going to correct our pressure for those attractive forces. Now we can look at our B term, and you will now see that we are taking a B term times the number of moles. This is actually correcting for the volume of the individual gas particles. So as you can see by this equation, as scary as it might seem, it is going to be a reiteration of PV equals nRT with just some corrective ideas in there. Our pressure term is being corrected for the attractive forces, and our volume term is going to be corrected by the volume of the gas particles themselves. Let's take a look and see how this will affect our math. Given that 3.5 moles of ammonia occupy 5.20 liters at 47 degrees C, calculate the pressure of the gas in atmospheres, first using the ideal gas equation. So we can do that using our PV equals nRT. So we have our pressure is going to be equal to nRT over V. So we have our number of moles, which is 3.5. We would have our R, so that is 0.08206. And finally, our temperature is going to be 320 K. Our volume in this case is going to be 5.2 liters. And if we were to do this math, you will get a pressure of 17.67 atmospheres. This is a calculation you've done many times. So now let's take a look and see how this gas actually behaves as a real gas and a non-ideal gas. So let us go and get the van der Waals equation. So we have P plus our AN squared over our volume squared equals, now the nice part about this is our nRT is the same, but remember that our volume must be corrected for by VNB. So let us go ahead and start to put in some of the values that we already know. So in this case, that would be 3.50 moles times our 0.08206 for our constant. And finally, our temperature is still going to be 320 Kelvin. But now our denominator is going to have a new value. So the volume in this case can still start as our 5.2 liters, but now we must subtract our 3.5 moles times the B value for our ammonia. This was on the previous slide, and you would be given any A and B value for the gases that you are needing. So this is 0.0371. So now if I were to solve for all of my numbers on the right side, you will find that I get P plus AN squared over V squared being equal to 18.13. So now what I will do is go and move all of my other corrective term over to the other side. So now I will get 18.13 minus, so now I need my A term for the ammonia, which would be given to you off of our table. That value is 4.17. So now I need the number of moles squared, so that is 3.50 moles squared over my volume squared, so that is 5.20 liters squared. And as you come to find out, the pressure of this real gas is actually 16.24 atmospheres. notice that there is a difference in pressure of approximately 1.4 atmospheres. This is a noticeable and drastic amount. So anytime you are working with gases and dealing with their dynamics, you can likely assume that we are going to use them as an ideal gas. However, if we state that we are using a real gas in real-world scenarios, it is best to use the van der Waals equation. The last thing that we're going to do for this lecture is look at these fundamentals of the kinetic molecular theory. So let's determine which statements are true. For number one, the most ideal gases have high pressure and low temperature. We know this to be incredibly false. Remember, we want our gases to be most ideal at low pressures and high temperatures. This will help us best for our kinetic molecular theory. So for number two, the van der Waals equation corrects for the number of moles of gas. This is not going to be true. Remember that it corrects for the pressure and the interaction of our gas molecules and the volume of our gas. It does not correct anything for the number of moles. Let's take a look at number three. Two gases with the same temperature have the same kinetic energy. This is true. Remember that they have the same kinetic energy if they are at the same temperature. This does not mean that they have the same velocity. And finally, for number four, effusion is the gradual mixing of two different gases in a container. This is not correct. This is actually the definition for diffusion. So if I look at my answer choices, you will see that I'm going to get answer B, which says that answer 3 is the only correct answer. In this video, you got a great description on how gases behave and the explanation behind them. This is really the cause of many of the properties that you have seen throughout this chapter. This now finishes up chapter 11 and is the last video of our summer course. Thank you guys for watching this. Have a wonderful fall semester, and thank you for your hard work. Have a great day.